Welcome to another mathematics lesson. We're investigating probability. Now, in the previous lesson, we wanted to ask the question, can mathematics help us predict the future? And we saw some tools that we could use that may be useful. Might not predict exactly the future, so don't get too excited. In this case, we're going to focus on situations when there are more than one thing could be predicted. So for example, will it rain as well as reach a temperature of above 25 degrees on a particular day? Those are two unrelated events, and we could put a whole lot of things together. Now, obviously, what you'd like to know is what would happen if we had 7 events, because that's the kind of number that will win you the lotto. But we're not going to go there today, I don't think. So let's have a look at what we're going to do and ask some questions about calculating the probability when we have more than one event taking place, either at the same time or shortly after. So, investigating the probability of 2 events, have you ever thought about, is it possible to find the chance of 2 events or more occurring, 2 or more events occurring? Well, if we look at our tools of probability that we've had, we recognize we know how to do some of these things. We recognize we know how to do the calculation of theoretical probability. We also recognize the idea of a sample space, and we're going to introduce and spend some time on this idea of a Venn diagram before we get to dealing with 2 events. So let's just go over some key ideas. So the first thing that I want to do is I want to talk to you about what is the sample space. Now, remember that when we were speaking about calculating probability, we said we wanted to consider all the possibilities that there were for a particular event or for a particular scenario or experiment. When we did the relative frequency calculation, we counted all the trials, the number of times you tossed or rolled a dice or tossed a coin. That will give you the total number of possibilities that will come out. So when we're rolling a dice, we recognize for one dice, there are only 6 possible outcomes. Either it can be 1, 2, 3, 4, 5, or 6. Now, what we recognized is all those values form the sample space. And out of those, we're going to select the ones that are the ones that we would like to have. Do you remember what we call the ones that we'd like to have? Of course, those are the favorable events, the ones that we are going to be the winners for. And so let's just make sure we've got the notation right. So remember, the sample space is recorded as a number S. The number of events in a sample is N, and then in brackets S. And here's an important relationship. The probability of something taking place in the sample space is the number in the sample space divided by the number in the sample space, and that's equal to 1, which tells us that whenever we've got an experiment and we don't make any restrictions, the maximum probability is 1. We know for certain it's going to happen. So whenever you see a probability of 1, you know you can be 100% sure. And that's a very important relationship. We're going to use it a little later. Right, let's have a look at the next term. Representing the sample space, we do it in a space like this, where we say, let's use a rectangle, and we're going to call it S. Now, within that sample space, we can put in certain other sets, smaller components. We refer to these as shapes, as a Venn diagrams. They can be sets that limit a certain condition that we're wanting to investigate or explore. So a Venn diagram goes into the sample space and focuses on our favorable outcomes, or the things that we would like to happen. Let's have a look at the notation. So we notate a Venn diagram with an X, and you can say that the number of things in a Venn diagram would be nx. The probability of X occurring, this is the theoretical probability, is the number of x divided by the number in the sample space. And our graphic representation of the sample space and x is simply the rectangle that represents all the numbers, all the possibilities, and x here represents those that we are most interested in. So that would be the Venn diagram for x. Now, if we were going to go a little bit further, it would make sense for us to do some examples to explore this idea of the sample space and Venn diagrams. And so I want to look at a little situation. Instead of pulling numbers out or socks out of a bag like I did in a previous lesson, I'm wanting to look at the letters of the alphabet. And we're going to divide them into different groups. Let's have a look at the criteria we're going to need. So we're going to let the sample space be the first 10 letters of the alphabet. And we're going to let set X be the vowels taken out of that first 10 letter set. So if we were to draw that, we recognize that we've got the sample space there with the 10 letters of the alphabet, and I think all of them are shown. And there you can see that X is only focused on the vowels out of those 10 letters, namely A, I, E. We don't go to the others. They're not in the sample set. So don't think you need to include O and U. No, they're not in the sample set. The sample set was only for the first 10 letters. And X, the Venn diagram that we've shown there, is only showing you 3 of the letters in the first 10, the 3 vowels that we've got. Right, let's move on. We've got that. We could say to ourselves, what is the probability of selecting an element from X? Well, that's not too difficult. We know that the number of elements in X is equal to 3. We also know that the number in the sample space is 10. And so if we were to calculate the probability, we'd recognize it's these two numbers divided by each other. And if we look at it graphically, we're going to take those ones and we're going to say, there we go, we've got 10 in the sample space, we've got 3 letters, and we take 3 divided by 10, which gives us a probability of 0.3. Now, that was really quite easy. Remember, this is the theoretical probability. And so we've been able to do many of these examples, but what's different in this case is that there is more than one favorable outcome. We could have A, E, or I as an outcome here, not just a black sock or a white sock. There's more than one possibility. But remember what I said, we wanted to investigate when we have 2 sets. So let's define a second set. Our second set will be will also be part of the Venn diagram, sample space. We're going to draw a Venn diagram. The first one was X. This second one we're going to represent as Y. And it's going to be the first 3 consonants of the alphabet. Do you remember what the consonants are? Those things that aren't vowels. So the consonants, the first 3 consonants would be B, C, and D. Let's see if I've got it right in my diagram on the Venn diagram. So there's the Venn diagram, and there we go. We've got B, C, and D. They belong to the set that we are going to call Y. And you can see that there is nothing in common between these two. They're quite different. And if we were to play a game, and we could say you could win if you draw either an element from set X or from set Y, well, then you've got a number of different options. Let's just make sure that we've got the idea clear about theoretical probability, though. I want to calculate the theoretical probability of selecting an element from set Y. So remember, we've got 3 things in the set, and we're going to calculate that. Notice that the sample space is still 10. We've got 3 in Y, and we recognize that it's going to be a third. So if we were to be very clear about that, we'd recognize we can calculate the probability of set X, set Y, and we can then come to some sort of conclusion about them. I want you to think about this. What would the probability be of calculating both of them? Maybe that's something to think about. I'm going to give you a few minutes to think about it. Take a short break, and we'll be back to explore that a little bit further.